The problem of Lab 5 was to explore Faraday's law by observing how a bar magnet falls through a conductive tube of aluminum foil, model this motion computationally using GlowScript, and compare the computational predictions to the observed data. Experimentally, I found that the bar magnet spent 0.79 seconds in the tube, and my computational model found a time of 0.346 seconds. This lab was done by dropping a cylindrical bar magnet through a roll of aluminum foil. The motion of the magnet falling through the cylinder was recorded using this video. The time that the magnet was inside the tube was determined. This was repeated several times to get an average time that the magnet spent inside the tube. Based on what we learned in class, I predicted prior to the experiment that the bar magnet's speed as it fell through the aluminum foil tube would be less than its speed as if it were to fall normally. The negative acceleration of the magnet should have decreased and approached zero as it fell through the tube according to my predictions. And I observed that the bar's motion was in line with my predictions, and its acceleration was slowed as I moved through the aluminum foil tube, although I do not think that the magnet was in the tube for long enough for its acceleration to reach zero. And in the rest of the slide report, I'll go over the physics principles, my results, and the model used to represent the real system. For the physics principles involved, Faraday's law says that in the presence of a time-varying magnetic field, there is an EMF whose magnitude is equal to the rate of change of the magnetic flux. Lenz's law says that the non-Coulomb electric field will drive a current in a direction to make a magnetic field that attempts to keep the flux constant. And so the time of changing magnetic field from the magnet is associated with a non-Coulomb electric field at the tube in an EMF, and the current direction and induced magnetic field direction is found using Lenz's law. And it's also developed with Newton's second law, which is the force of gravity. Here we can see Faraday's law and the equations for EMF, and here we can see the direction of the non-Coulomb electric field. For my results, here you can see the dimensions of my magnets and my tube. Here's the mu value 0.48 that we calculated from Lab 3. And so experimentally, I found the average time for the magnet to pass through the tube was 0.79 seconds. My computational time was found to be 0.346 seconds, and my free fall time was found to be 0.22 seconds. So here's the model I used to represent the real system. The code takes in the dimensions of our aluminum foil and the mu of the magnet we found in Lab 3 and models the motion of the magnet as it falls through the tube. It is modeling the foil tube as a stack of rings and finding the magnetic field to the magnet at each loop. It then finds the flux of each loop and sums all these together. As the magnet moves, the computer updates the calculations and updates the position of the bar magnet. Finally, it calculates the time the bar is in the tube and outputs a graph of velocity versus time. So here we see the graphs. This is my graph when mu is equal to 0.48. Here you can see that the calculated time is much lower than the time I found experimentally. However, when I graph with the mu value of 0.08, we get a better graph closer to the time I actually found experimentally. And so our graphs show exponential decrease, and this is because the bar magnet is still accelerating in the negative direction with gravity. However, the upward induced force is decreasing that acceleration, and as you can see, the velocity is approaching a constant value, meaning that the acceleration is going to zero, which will be its, and so it's approaching its terminal velocity where the acceleration would be zero, and this decrease in acceleration is caused by the upward induced magnetic force. And so in the simulation, as the bar falls, we see two colored rings, a blue one below the magnet and red above, and so this shows the direction of the induced current in the tube. Red is counterclockwise and blue is clockwise. And so the possible reasons of error for my values are that I have a bad mu value from Lab 1, or that my magnet was hitting the side of the tube. So what's happening in this lab? So what's happening physically here in this lab? So as the bar magnet falls, its magnetic field acting on the tube changes. In this case, I draw the bar magnet with the north pole facing down for each trial, so the magnetic field is pointing in the negative y direction, and dB/dt is positive in the negative y direction as the magnet falls, so the B field gets stronger as the magnet gets closer to the tube, and this means that flux increases in that direction even though area is constant. Flux is increasing in the negative y direction, so induced current generates a B field in the positive y direction to counteract the change in flux based on Faraday's and Lenz's law. And the induced magnetic force back on the magnet increases until it will be equal to the force of gravity, and the bar magnet moves at a constant speed if it's in the tube for long enough. And this is why we see exponential decay in the graph. And had I flipped the magnet, the time to fall would be the same because the induced field would be the same. And here you can see the important aspects of code. Here I'm finding the magnetic field of the magnet. Here I'm finding the change in magnetic flux. Here I'm finding the typical magnetic field at each magnet. And here I'm updating the position of the bar magnet. So for my conclusion, For the conceptual questions, if the resistivity of the conductor were reduced as close as possible to zero, the current in the tube would increase greatly. So the flung magnet's acceleration would be slowed even faster, and it would reach terminal velocity much faster because current and force are proportional in this case. And if holes or slots were cut into the tube, the rings would no longer be complete, and you would essentially have a break in that part of the circuit. So the ring currents would decrease in magnitude in my circuit, and there wouldn't be any current present below the break or hole in the loop. And this reduced current would mean less induced force in the flung magnet, so it would decelerate less. And so in this lab, we saw a really cool physical property and learned a lot about Faraday's law. Thank you.